Okay, now on the screen, Jesse sent this in. Now listen, this is what I'm expecting to get back. Somebody sent me one and tried fudging me already. Well, they just took their old one, typed in the answers that were on there, and sent it back to me. But it didn't say grade sheet locked. No, this person used the original one. And I caught it right away. It's like, so when you get this, you cannot type into this, right? So when I open it, the very first thing I do is I click here to make sure that's still locked. So if you haven't done this, please do this. It's going to take you a minute to put your name in here. 3 numbers, 5 numbers. Look, you can compare. It's not going to self-grade it, although I should do an if-then statement and self-grade it, but this is the points for everything here, right? Maybe I'll get there.
Well, I'm not going to email you a copy of anything this week. I'm old school. Oh, yeah, I'm just walking through that door. I've already got it done.
Okay.
I just didn't know I had to email it to it. It did not state that.
Now, let's review what we did last time.
He outright stated that you had to have points
These values here are specific heats. These values tell us how many calories to heat up 1 gram a degree Celsius. The higher the number, the more energy it takes to heat something or cool something. It works both ways. Lucky for us, water is 1. So you can see we can heat up lead in a very short amount of time, 0.031. Then I have to stress where we left off.
I need to talk to you about some things. What you give us in the homework and what this says.
They might be, the charts might be off of here. Hopefully they're close. Now, we're going to do another calculation that we do heat lost equals heat gained. Now, you just got to reason this out. If this is going to lose heat, you want to keep this quantity in parentheses, your change in temperature, a final number. So you know, since this is going to lose heat, if it starts at 150, T final is going to be less than 150. So that when you subtract it from 150, you get a positive number here, correct? And over here, you know that if the water starts out at 20, it gains heat. It is going to be larger than 20. So we're going to go T final minus 20. That makes it work out great. Otherwise, your book just sets everything to 0, and they throw a negative heat on one side, and it just makes it too complicated. Yeah. So, just make sure you can use either one, provided that your specific heat value matches. So these are the same units here. You could use kilocalories per kilogram, or you can use calories per kilo. This would be the same thing. Because in one, you would multiply it by 1,000, and then you divide by 1,000. You're going to get the same number in kilocalories per kilogram. Doesn't matter which one you use, but if you write in your units, you know the units have to cancel out, right? Yeah, so it doesn't matter. Now, yeah, you're going to have to get a chart like that on the test. Yep. Now, this mentions specific heat of gases, and we could actually do gases. But we're not going to calculate gases out. Now, we talked about this a little bit. The internal energy, how much vibration there is of these molecules back and forth hitting each other, but also within the bond. So if you have nitrogen and oxygen that are bonded together, these are vibrating back and forth and things like that. Now, here is what you're going to do for lab, calorimetry. So basically, again, it's going to be heat lost equals heat gained. I showed you the calorimeter last time with a stirrer in there. This does not have the bomb in there, the metal jacket that I showed you, but you're going to have a thermometer. You'd have the metal jacket in here, or the bomb part, a stirrer, and you could actually calculate food calories. And that mentions that. Now, here's what we need to talk about. This. So, this shows us ice. Now, we are heating up ice. You take ice out of the freezer. What temperature is it at? In this diagram, it is at -40. Now, the first thing you have to do, if you're going to calculate the total heat it takes to take ice at -40 to, let's say, steam up here at, boy, it doesn't even go on my chart. I better fix this up. So it looks like you're going to get to about 140, maybe. Let's say this matches at 140. This involves quite a bit of calculating. This part right here, this curved line, you're going to have to calculate how much energy goes into heating up ice as it stays a solid. So this part right here is going to be your mass of ice, specific heat of ice, change in temperature of the ice. And what is the change in temperature of the ice going to be? What temperature is ice going to melt? In Celsius. 0. So this change in temperature is going to be 40, right? Ice has a specific heat, liquid water has a specific heat, and steam has a specific heat. So we know this, we're going to have to heat this up 40 degrees. We're then going to have solid ice. Once you have solid ice, you have to melt it. This is a flat line. This right here is our melting. Now I'm going to put this. This is melting, our ice. This temperature does not change. Since the temperature does not change, all we need is a mass and then how much joules it takes per gram. Right now, well, this is solid ice at -40. At this line right here, we have solid ice at 0. When it melts, it stays 0 until it's done melting. Then you're going to have liquid water at 0, correct? And that's a good question. I should have followed this up. Then you're going to take liquid water from 0 to 100. Now look at this flat line. Check this out. This is significant. This is the same amount of grams. But look at how much heat it takes to heat your water from 0, this is liquid water at 0, to water gas at 0. Or you could say you're boiling the water away. It takes a lot of energy. Or excuse me, at 100. This is at 100. So this is getting liquid water up to 100. This is taking all of that liquid water and converting it to a gas or steam at 100. Then we can heat up our steam, can't we? And notice this is flat. The temperature doesn't change when you boil water. So here's a question. You have boiling water on the stove. You let it boil another 10 minutes, it's hotter, right? No, it's the same temperature. It stays the same temperature, correct? If it's boiling, it should be 100, no matter what. Now, how much energy it takes to melt it over here, this is enthalpy of fusion. We got another symbol. This is enthalpy of fusion. This is the same value it would take to freeze it or melt it. Now, again, there's no temperature change because it stays the same. In the next chart has that.
So instead of that word you just said that I've never heard before in my life, I'm just going to say heat of fusion, right?
You could say,
Or melt out.
right here's our heat of fusion. Yes. Heat of fusion, here's kilograms per, or kilocalories per kilogram. Okay? Now, that has a specific value. In fact, we can put these numbers, we can put these numbers in. We can see what they are. It's 20 kilocalories of heat to heat up your ice, right? To get your ice at 0, that's a solid ice, to liquid water at 0 is going to take how many? 80 kilocalories, correct? Now, we need to heat liquid water from 0 to 100. So this right here is going to be the mass of H2O. Specific heat, H2O, and the change in temperature of the water. And we know that that change in temperature is 100, right? So it looks like that takes 100 kilocalories. Now, this flat line right here, since the temperature doesn't change, this is going to be the mass times the enthalpy to vaporize it. We use this vapor here, fuse it together here as ice. So fusion is with your melting or freezing. This right here is if you're boiling it away or you're condensing. Now, let's talk about this. Let's talk about the length of this line for a second here. If you've ever making something on the stove and you're cooking spaghetti or something and your water's already boiling and you stick your hand over it so that the steam is coming up from underneath and hits the bottom of your hand, that's hot in a hurry, correct? That's about the worst it can be because it takes all of this energy and it's taking steam and it's converting steam, the reverse of this, to liquid water. Where is it dumping that heat energy? Into your skin. According to this, yes. Because there's a heck of a lot more energy here. Now, I used to work at the Old Galley Cheese Factory. all these milk plants had a steam line and a cold water line. So to make hot water, you just mixed them. So you have a hose in your hand. To make hot water, you better not turn your steam on first. You turn your cold water on, then you turn your steam on so they come together, and that makes your hot water. And when you turn that off, you better turn your steam off first, then your cold water, because if you turn your cold water off first, you've got just steam coming out. And you can do tremendous burns and damage with steam. The amount of heat energy that it takes from your skin immediately is an astronomical amount. Steam burns are the absolute worst. Absolute worst, steam. No, I yelled a few times because I screwed up, but they're in plants where you get boilers that actually blew up in some of these plants years ago. Steam was bad. The whole boiler would blow up.
In some slaughterhouses, they use steam slicing area where all the innards come out. Because of all the infection. But it's steam water, not straight steam. And yeah, it has to have cold. Not anybody burn, but I watched it.
Now, this right here now is another calculation. This is going to be your mass of, I'm going to call it steam, specific heat of steam, and change in temperature, right? So you're going to have to do a calculation like this that you would have to do 1, 2, 3, 4, 5 calculations of heat. You'd have to add these all up. The mass can change. We are not. Okay? So now, again, I want to stress that you have 3 specific heats for H2O. H2O in the ice phase, H2O in the liquid water phase, and H2O in the gas phase. What's that? Any material, yes. By steam, I'm saying H2O is a gas. Now, we can have the same thing down here. You have to know the boiling points and freezing points, so this chart actually has it. So we can take actually lead. Lead melts at 327. The heat of fusion, if you're going to melt it all, so the melting point is 327, so you'd have to take it from 20, and this is easy to do. You can melt lead on a hot plate. Lead has a low melting point. So you'd have to get it up to 327, and at 327, that solid chunk of lead is going to stay the same temperature until it's entirely melted, correct? Then you got to take that up to the boiling point, which is 1750, and then you could boil the lead into the gas phase if you had a high enough temperature. So this works in reverse as well. So if you take water, boiling water from the stove at 100, throw it into the freezer, you have to take all this energy out, and this all would have to go backwards, right? Which is what your refrigerator or freezer is doing all the time. It's taking energy out. Yes. Okay, so we've got something like this. Wow. We've got something like nothing, like we're out of time. We'll finish this Monday. We'll be done with this. I'm going to work on getting your other stuff out then for the next chapter.